Okay, welcome back to another 510 video. I guess this is technically the first 510 video. Um, this week, that is the week of the first homework, I'm not going to do a ton of video, and I'm probably not going to do a bunch of detail in the videos that I do, and I'm not going to do too many examples, if any, honestly. The reason for that is that we're largely doing review, especially this first week and probably a few after that. So I don't want you to spend a lot of time watching videos. I do want you to do the assigned readings, but honestly, I'm not. Do the readings from Wasserman. Probably don't need to do the optional ones unless you really need a deep dive into some of the refresher material. I want you to spend time working on the homework. And most importantly, if you run into trouble doing the homework, I want you to come to office hours. And with such a small class, we should be able to individually help you through whatever problems you're having. So I don't want to spend a time doing like a ton of recorded video only to have no one use it because you already knew all this stuff. I would rather do a sort of minimal amount of video and then work with you individually on Piazza and office hours to sort of fill in the gaps. So going to do a couple of videos this week just to sort of jog your memory about some important definitions and theorems, that kind of thing, that you should have hopefully seen before. Okay, so before I hide myself here, just a little bit of context about where we are and what we're doing. So, hopefully, somewhere you've seen this picture before, and it looks something like this. We have a circle here, and we have a circle here, and on this side you have some data that you've observed. The left-hand side, I'm going to call the data generating process, DGP for data generating process. Some people would write population in this circle, but basically, ultimately, the thing that's in this circle is some probability distribution that sort of like describes the world. And then somewhere, probably prior to this class, you had a class on probability and a class on statistics. So a class on probability focuses on going from this circle to this circle. So think of it like this. Like you could say, well, the data generating process for this particular example is something like, I don't know, a binomial distribution where n is 10 and p is 0.6. And then you could ask a question about the right-hand side, which is like, well, what's the probability that we see, I don't know, something like 70 successes in 100 trials, something like that. So we can ask questions about like, well, given that we know the data generating process, that we know the distribution, what's the probability that we see a certain data set on the other end when we do some sampling? And so that'll be sort of the focus of the first few weeks of this course, is sort of refreshing all of that information. Because at the end of the day, that's mostly sort of a bunch of definitions and theorems that are going to help us along the way. And probability is sort of the language that we'll use to describe a lot of what is going on in the next thing that we're going to talk about, which is going the other direction. So where we're going to ultimately want to focus, and what the whole field of statistics really tries to focus on, is going the opposite direction. So we live in the real world now where we can collect data, but we can't play God and say, well, we know the data generating process. We want to infer it. So going this way, that's what we would call statistical inference. Oh, I can't even spell statistics. Statistical. So that's what we're all about here. That's what we want to do, is we want to say, well, here's some data. What is the nature of the world? And because there's going to be some uncertainty around that because we understand that for different samples we could get different data. We need probability so that we have a language to describe this uncertainty. When I was just saying all that, I thought of something that I want to, I think, actually give its own slide. So many years ago, I was an undergraduate student at the University of Illinois, and I took a class called Math 347. Great class, highly recommended. And that class, it was scary. It was, I mean, the whole point of that class, it's your first foray into, oh, here's what math really is. It's not that calculation stuff you did in high school. It's talking about, proving things and stuff like that. And do I remember everything I learned in that class? No. But I will never forget something my professor said, and it was this. And oh, was he right? I'm gonna have to spell check that before I release this video, but that was Marius over in the math department at Illinois here. I really need to walk across the street one of these days and tell him that I still recall this story, but he was absolutely right. So, when you're doing mathematics, you have to rely on the definitions because otherwise you can't express what you're talking about, and you have to rederive everything from axioms. But so what I'm saying here is that what we're going to talk about in this video is some very basic definitions and theorems from probability. And these things are your friends in that you're going to have to constantly rely on them to accomplish the tasks we need to in this course. So I'm not saying memorize all the definitions and theorems, although some of these basic ones we're going to go through in this video, I kind of hope that you're familiar enough with that if you don't have them memorized, your recall of them is very good. But know that they're there, know that they will support you, and you're always going to have a textbook or something to look them up in. So do go seek their help. Okay, let's get started. So I am going to, I literally am looking at it right now. I'm going to follow along through chapter 1 of Wasserman in this video, where I'm essentially going to give you the greatest hits of the definitions from that chapter and riff a little bit on them to hopefully sort of give you some intuition and jog your memory a little bit. But I highly recommend you actually read the chapter in addition to watching this video. The order you do that in, I don't actually think is that important as long as you do the reading. Okay. I'm going to get rid of me so I have a full board to work with here. And I'll check in again at the end of the video. Okay. So if what we're here to talk about is probability, I think the first thing we should probably define is probability. So a definition. So right now, when we're talking about probability, we're talking about it in a mathematical sense. So we're not going to sort of rely on any particular interpretation of probability. That is, we're not going to be a frequentist in this moment. We're not going to be a Bayesian. All we're going to be is a law-abiding citizen. And so what I'm going to essentially lay out right now are the laws of probability that we will never, ever break. So let's say we have some function p. And this function p assigns some real number to any event a. So this function p then is a probability distribution if three conditions are satisfied. So first, we need that for any a, the number that this function returns is greater than or equal to 0. So again, for any event a, the probability has to be greater than or equal to 0. There's an obvious consequence of this, which is that you can't have a probability that's less than 0. Hopefully you knew that already. All right, 2. The probability essentially that something from the sample space happens is 1. So I sort of skipped over a little bit about set theoretic notation here, but that sigma that I just used is the sample space. Which is the collection of all possible events. Okay, one more rule here. So lastly, we're going to consider multiple events at once. So if A1, A2, A3, so if these are all disjoint, then we can say something about the probability of one of these things happening, which is that the probability of the union is the sum of the probabilities of the individual events. Okay, so these are what we would call the probability axioms. They're often attributed to Kolmogorov. So yeah, basically, if we just start with these three rules, we can derive the rest of probability. We're not going to do that. We're just going to sort of state some of those consequences of these rules as soon as I take a sip of water here, because again, start of the semester, I'm not used to talking so much. Okay. Oh, I should also note that obviously my handwriting is not too great. Obviously, I'm not writing down every word I say, but again, for the full detail, the reading has exactly that. Okay, so I'm going to quickly jot down some consequences. So the probability of the null set would be 0. So essentially, if for some experiment, the probability that nothing in that experiment sample space happens, that's not possible, right? Something from the sample space has to happen. So if A is a subset of B, then we have the probability of A is less than or equal to B. So if B contains all the possible outcomes that A does, well then of course the probability of B is at least as much as A. Probabilities, you've probably heard, must be between 0 and 1. Let's see. The complement rule. So the probability that A prime happens is 1 minus the probability that A happens. This is quite possibly the most frequently used probability rule. I'm pretty confident that if you're watching this video, you've seen this before. Some people might use a C instead of a prime symbol, but it's the set theoretic notation for the complement. Right. So if the intersection of A and B is nothing, then we have the probability that A or B occurs is equal to the probability of A plus the probability of B. Okay, but that importantly is only true if this condition here is met. More generally, if we just have any two old events, A and B, we get something slightly different. So there we go. So the issue here is we're doing a little bit of overcounting, and that's why we subtract off this intersection here. And you can see now that the previous rule was simply a special case of this, because if A and B are disjoint, then the probability of their intersection is 0. Okay. What's next? Okay. Another definition. I'm going to stop writing the whole word definition so you don't have to see me constantly almost make a spelling error. So the next thing we want to talk about is independence. So let's say we have events A and B, then they are independent if the probability of A and B is equal to the probability of A times the probability of B. And there's a generalization of this if you have more than one event, but we're going to ignore that for now. And note a couple things about independence, which is that this definition is the definition, but it won't be the only one. And in my opinion, it's not the most intuitive. More on that in a second. But sometimes we need to think about independence a little bit. Sometimes we assume independence. And if we assume independence, well, then we can use this fact in a proof or something. Other times, we check for independence. And then we don't know if this is true, and we check if that's the case, and if it is, then we say they're independent. That's something we need to keep in mind. Every now and again, a student will sort of like work themselves into a situation where they need to be assuming independence, but they're trying to check independence, and that kind of becomes pretty hard when it's independent because we said it's independent. So that'll be something you want to keep in mind. Okay. Another definition. Probably one of the more important definitions in this course. So let's say we have events A and B, and we're going to say we know that the probability of B is greater than 0. Then we have the conditional probability. We say of A given B is the following. So we have, which order did I do? A given B. So the probability of A given B is the probability of A and B divided by the probability of B. Okay, so right, that is what we call conditional probability. We will use this definition nearly constantly. Sometimes it'll be sort of lurking in the background invisibly, but a ton of what we do in statistical inference is a conditional analysis. So conditional probability is extremely important. One thing to note here is that conditional probability itself satisfies the probability axioms, whereas we can't flip this. So something like if you were known A, this does not satisfy the probability axioms. But more important than that is a new way of looking at independence. So if we have A and B are independent if and only if probability of A is equal to the probability of A given B. This to me is the much more intuitive way to think about independence. Because if you think about what this statement right here says, the probability that A occurs is the same if we know whether or not B has occurred. So essentially, I don't care what you tell me about what happened with event B. The probability that A occurs or not is still the same. So for checking independence, you can use either definition, but for understanding what the concept is sort of about, I think that this definition is much more useful. Okay, so now we come to maybe one of the most important things we've seen. So important, we'll call it a theorem, which is Bayes' theorem. The apostrophe is after the S because this is named after the Reverend Thomas Bayes. Okay, so before we write down the end result here, I want to... am I going to have enough room if I do that? No, I'm going to draw it over here. I'm going to draw a sample space. And now what I'm going to do is I'm going to chunk up the sample space into disjoint and exhaustive sets. So something like this. So I'll call this, so this portion of this whole sample space is called A1, A2, A3, A4, A5. Cool. So now what I'm going to do is I'm going to overlay another event, which I'll call B. Okay, cool. So now note that, let's, for example, talk about this right here. So this is the region A5 and B. And so similarly, this would be A4 and B. This would be A3 and B, A2 and B, A1 and B. So this gives us an alternative way of writing the probability of B. So what we can do is we can say, well, the probability of B is equal to, we'll sum up over however many disjoint regions we have. I'm just going to use n instead of 5, but in this particular case, it would be 5. The probability that each, there should be an I and B, right? And we can go a step further. Actually, we can go back because I forgot to write something. Let's go back here for just one moment. If I rearrange this equation a little bit, I get the probability of A and B is equal to the probability of B times the probability of A given B. So the way to think about this is to say, well, the probability that A and B occurs is the probability that B occurs, and then given that we know that B occurred, A occurs. That's I need that right now. Sometimes this is called the multiplication rule, but it's really just a rearrangement of the conditional probability definition. Where was I? Right. So then we can write this I'm going to basically expand this out with the conditional probability rearrangement I just said. I should have, that's okay. Anyway, so I want this in terms of B. So this will be the probability of B and each A times the probability that we're in each A. Okay. This statement right here is often called the law of total probability. It's basically just a way to decompose one probability into a bunch of other ones. Except I should probably write it correctly. That's a conditional there. I'm going to leave it blue just to highlight my mistake. Okay, so now I want to write down Bayes' theorem finally. I'm going to try to do it on this page so we can see all this at once. So what did I say here? So we have A1 through some, I'll call it, I'm going to stick with the book's notation. So we'll say K. Pardon me. I'm going to change these N's to K's real quick. It's arbitrary, but I just want to be consistent. So this is what we call a partition. Which again means that A1 through K are all disjoint, and their union, that is taken together, they are exactly the sample space. Okay. Then we also want probability of B to be greater than 0. Now we can finally write down Bayes' theorem, except I'm not going to write down Bayes' theorem. So probability that some A given B. So the point of Bayes' theorem, well, I guess I don't want to say there's a point to it because math is just statements of fact. I don't want to say there's a point. But what it'll do for us is it will flip the conditional. So what I have here is a probability of the form A given B. What I want to do is now write an expression where I have conditionals more of the form B given A. So to get there, though, I'm going to first apply the conditional probability rule. So that said, this is equal to the probability of AI and B divided by the probability of B. So again, all I've done is applied this definition. Now I'm going to apply this definition to the numerator here, which means that I will have the probability of B given AI times the probability of AI divided by the probability of B. Okay. And now the last step will be to replace this probability of B here with the law of total probability. So we end up with, try to write this one a little bigger. Something like that. Except because I used A above, I should probably be using J's here. Otherwise, the indexing is going to get really messy. Sorry. Okay, there we go. All right, so that's if we go straight from here to here, that is what we would call Bayes' theorem. Yeah, so it's a theorem because it's extremely important. This is so important, later in the semester, we'll see an entire branch of statistics where every single thing they do goes through this formula. That's called Bayesian statistics. It's not that frequentists don't use this, it's just that they don't use it as the basis for all of their analyses. When we get to Bayesian statistics, we'll give certain quantities here, particular names, but for now, this is just a statement of mathematical fact about how to perform a certain probability calculation, but later on we'll give sort of interpretation to this and use it as part of statistical inference. Okay, so yeah, was this an informative video? Probably not. If you haven't seen these things before, hopefully you have seen these things before. Hopefully this is jogging your memory about these things, and hopefully when you then, oh, I wanted to say hi. Hello. So hopefully when you see these things on the homework now, you know, you'll start making the connections again, and this stuff will all come flooding back. Okay, so I'm going to cut this video here, otherwise it'll go on forever. If you made it to the end, good job, and I'll see you in the next one.